A very good day to one and all. Myself, Ruchika Batra, Associate Professor, IITM College, Janakpuri. I'm going to give my presentation on data compression techniques. Basically, these are used for text-based algorithm. You can also use them for images, audios, and videos. When we talk of data compression, that means we are applying compression techniques to send the data through different mediums, maybe internet, maybe web, or any other medium. So, first of all, what is compression? The process of coding that will effectively reduce the total number of bits needed to represent certain information is termed as compression. The compression techniques take care of that your data, which is of high volume, is reduced and sent through different medium. You provide the input data, the encoder or the compression technique compress the data, the storage or network where from wherever you are transferring the data, pass the data, and on the receiver end, the decoder decompress the data to its original size. The objective of this presentation is to distinguish between lossless and lossy compression techniques, then describe run length encoding and how it achieves compression, describes Huffman coding and how it achieves compression, describes Shannon fano method of encoding and decoding. Then we have Linzel-Wells, that is LZW encoding method, that is the use in dictionary encoding and decoding. Data compression implies sending or storing a smaller number of bits. So the bits can be your information of your image, information of your audio, video, or your text material. Although many methods are used for this purpose, the general methods can be divided into two broad categories, that is lossy and lossless methods. Lossless methods basically apply for text or programs, and they are further subdivided as like run length encoding, Huffman encoding, LZW, then we have Shannon fano. And lossy methods includes for image, audio, and video, and they are like JPEG, MPG, MP3, and so on. When we talk of compression ratio, it is given as B0 by B1, where B0 is the number of bits before compression and B1 is the number of bits after compression. The entropy is given as minus Px log to Pxi, that is the weighted average of the number of bits required to encode the symbol of a message. The entropy of the entire message is the sum of all this weighted method. Now, when we talk of lossless, that means that the data is not altered or lost during the process of compression or decompression. The original image and the new output data, both are same. It is used to save disk space. The compression ratio may range about 10:1 to 30:1. When we talk of lossy compression techniques, it results in loss of information. The human fill this information by some redundant bits or some other value. It is basically used for audio, video, and color images like JPG, MPG, DVI, H261 are some of the well-known methods. Coding techniques can be entropy based or source based. Entropy based again have repetitive sequence like run length encoding, which we'll look further in this slide. Then we have statistical encoding like Huffman and LZW, which we will also be looking in this slide. Then we have source like transform, FFT, and DCT. Then we have differential techniques like PCM, delta modulation, and ADPCM. Apart from that, we have vector quantization method, which restores the bit information. Lossless compression, which is we are going to discuss in this slide, is the compression method that restrain the integrity of the data, and the original data and the data after compression and decompression are exactly the same, because in these methods the compression and decompression algorithms are exact inverses of each other. No part of the data is lost in the process. Redundant data is removed in compression and added during decompression. That means encoding will take care of that. Whatever data you have reduced, the decoding method adds that data. Lossless compression methods are normally used when we cannot afford to lose any amount of data. First example of this is run length encoding. It is probably the simplest method of compression. It can be used to compress data made of combination of symbols, and it does not need to know the frequency of occurrence of those symbols. If the data is represented as 0 and 1, this is the most efficient scheme. The basic idea behind this method is to replace every consecutive repeating occurrence of the symbol by one occurrence of the symbol followed by the number of occurrences. That means how many times a character or an alphabet has been repeated, you will just represent that. So this is a simple method, and as you can see, we have the original data with number of time b, 9 times b, then 16 times a, then only one time n, and 10 times n. So the compressed data, you can see this long bits of 32 has been replaced to b9, a16, n1, m10. It's a very small number, it has reduced. But in this technique, you can only apply this technique when the data is, when we have more redundant data in a data set. Another example of this is like you have 14 0, so you are giving the binary value of 14, then 1 is considered as a separator, then you have 4 0, so you represent it in the binary octal term. Since 1 and 1 given and there is no value in between, so that means there is 0 0, so we have given 0 here, again 12 0, so by the octal format of 12 is binary format of 12 is given in the table. So you can see the compressed data has again reduced the 16 digits to 14 plus 4, that makes 18, and 18 plus 12, 30 bits to just 16 bits. So that's again a big redundant. The repetitive sequence algorithm like run length encoding is very widely used and simple compression technique which does not assume much of memory resources. Another example, we can see this A one time, C three times, B two times, again A three times, and B two times. So how you want to represent that? That way you can represent the data. Second algo which we are going to discuss here is Huffman coding. In Huffman coding, we assign shorter codes to the symbols that occur more frequently and longer codes to the symbols that occur less frequently. For example, let us assume that our text file contains only 5 characters, namely A, B, C, D, and E. Before we can assign bit patterns to each character, we assign each character a weight based on its frequency. So you can see A has occurred 17 times, B has occurred 12 times, C 12 times, D 27, E 32. So the major occurrences of E and the least occurrences of B and C. So we will give frequency code, smaller code to E and larger code to B and C. Let's see how we are doing that. As seen, A, B, C, D, E, we are representing as nodes. So we will combine the shorter one first, like B and C combined together makes that 24. So we have combined them. Then the next shorter one is A, which we are combined with B and C and keeping the tree simple and balanced. Then next one is D, but moving to D will make the tree imbalance. So we are combining D and E, and the total of D and E we combined, and there is a value 100 of all together. Now we can assign codes to these, frequency to these. So if as we move in the B tree, we have 0 assigned on the left side and 1 assigned on the right side. So we can give 0, 0, 0, 1, 0, 1 this way. And now how I represent A is 0, 0. How I represent B is 0, 1, 0. How I represent C is 0, 1, 1. Now E is 1 1, D is 1 0. So it's just simple codes. And as I told that E has the major value 32, so it will have the smallest code. You can see E has the smallest, D has the smallest, A, and the one with having least frequency have the larger code. So this is how we assign value. Now how we perform the encoding and decoding? In encoding, whatever the character is, we place the character with its value, like E has value 1 1 1 1, A has value 0 0, so we can represent it by 0 0. Then next E again we have the value 1 1. So similar way this is continue. When we decode, this is the Huffman code. We will take the values from the decoder and assign the text value. As we can see, the original text and the output text is same, so there is no loss of data. That is why it is known as a lossless technique. Another algorithm which we are going to look here is Shannon fano algorithm. It is also known as entropy encoding technique for lossless data compression. It is named after the two well-known scientists, that is Claude Shannon and Robert Fano. That is why the name Shannon Fano. It involves some steps. The first step says that for every given list of symbols, develop a corresponding list of probabilities or frequency counts so that each symbol relative frequency of occurrence is known. That means whatever symbol we are taking, like we can take A, B, C, whatever symbol we take, we give an probability of occurrence of the symbol or the frequency of the symbol, we assign a table where we have the symbol and its probability or frequency. Now we sort the list of symbols according to frequency, with the most frequently occurring at the left and the least common at the right. This is how we divide the two. Then we have the next step as divide the list into two parts, with the total frequency count of the left part being as close as the total of the right. It is not majorly that both the left and right sides will be equal, but they should be balanced. The step 4 says that the left part of the list is assigned the binary digit 0 and the right is assigned digit 1, as we do in the tree structure also. Now we recursively apply the steps 3 and 4 so that each of the two halves subdivided groups, and adding bits to the code, we will get the probability value. So we can say A has the probability value of 15, B has the probability value of 7, C has the probability value of 6, D 6, E 5. So we will have a combination in such a way that if I combine A and B, that is 15 plus 7, the sum total of which gives me 22. Then 6, I can combine C, D and E, that is 6 plus 6, 12 plus 5, 15. So they are nearly equal. Or I can say another probability like 15 plus 6, that is nearly 21. And we can combine 7, 6 and 5, that is equal to 6, 5, 11 and 7, 18. So 18 and 21, almost they are balanced. This way we can combine and divide our tree. Once we divide the total values, you can see these A, B we can combine, C, D, E we can combine and assign the values. So 0, 1, 1, 0, 1, 1, as we have done in the Huffman coding, we can give the codes to them. Or not even this combination, we can combine AC and BDE also. So anyway, you can combine these trees and make the structure. The encoder and decoder is same like Huffman coding. Another method is LZW encoding, which is named after the three scientists Limpel, Ziv and Welch. It is another lossless compression technique. It tries to identify the repeated sequence of data and add them to the code table. It is also known as a dictionary-based encoding method. The idea is to create a dictionary or a table of string used during the communication session. If both the sender and the receiver have a copy of the dictionary, then the previously encountered string can be substituted by the index in the dictionary to reduce the amount of information transmitted. Now, how we can present this? The basic idea is to create a dictionary or a table, and if both sender and receiver have a copy of the dictionary, then whatever the previous encounter string can be substituted by their index value. Let's see the algorithm. We will extract the smallest substring that cannot be found in the remaining uncompressed string. That means if I have A, B, A, B, so the smallest is A. So this is the first one I'll take. We'll store that substring in the dictionary as a new entry and assign it an index value. The substring is replaced when the index found in the dictionary. So whenever the substring occurs, I'll give the index value from the dictionary. Insert the index and the last character of the substring into the compressed string. The compression technique says that in this phase, there are two concurrent events. We have to build an index dictionary and compress the strings of symbols. The algorithm extracts the smallest substring that cannot be found in the dictionary from the remaining uncompressed string. That is, whatever the data is, I'll take the first smallest occurrence of the data. It then stores a copy of this substring in the dictionary as a new entry and assign it an index value. The compression occurs when the substring, except for the last character, is replaced with the index found in the dictionary. The process then inserts the index and the last character of the substring in the compressed string. So we can see if my data says B, A, B, A, B, 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 A, A, then again 4 times B, A. So first smallest occurrence, which is not compressed or repeated anywhere, is B. So I can say B as the first symbol and give it as the index value 1. My second smallest is A. I can represent it as 2. Then another AB, which is not repeating and I have not taken before, is I can give a value as and store as 3. But since A has first been, now what I said, with whatever is the first occurrence will be as it is, and then we will have the character. So first occurrence is A, so A's value is 2, and the next character, last character B is 2. Then another further substring we have ABB, which is not further divided, so ABB. Now we have the value of AB as 3, so we'll take 3, and the last we will keep as it is, that is 3B. Again, we have the next character as BA, which cannot be further subdivided. So BA, we have the value of B as 1, and A last occurrence we will keep as it is. Another is ABB, that is A and 3 times B. So we have the A and 3 times B value as 4, and the last B will keep as it is. The last occurrence is BAA, where we will take BA as the value 5, which is already there in the dictionary, and A, the last character, we will keep as it is. So we can see the uncompressed data, which is so long, is now compressed into these shorter bits. For all these compression techniques, one thing is for sure, that we need redundant data. The data should have more occurrence of frequency. Now, how we decompress the data? It is the inverse of compression technique. The process extracts the substring from the compressed string and tries to replace the index value with the corresponding address in the dictionary, which is empty at first and build up gradually. The idea is that when an index is received, there is already an entry in the dictionary corresponding to that index. So if I take B, I'll take B, pass string B, and pass it. Then again I take A pass string, I give it a value. Then 2B, I'll add the value of 2 means A and B as it is. Then next value 3B, I'll take what is the value of 3, and similarly we will continue pass these strings. The pass data goes and it takes the value from the index location, the character set from the index, and we will get the original thing. Again we can see this decompressed data, the output data and the input data is same. So we can say that this is a lossless technique. Advantage of LZW algorithm is it is simple and fast. It is a lossless compression technique. That means no data is lost during the communication. The whole algorithm can be expressed only in few lines. There is no need to analyze the incoming text. Whatever the text be, you compress, take the uncompressed data and start compressing from the first occurrence, first character occurrence. The LZW excels when used for data streams that have any repeated strings. As I have already told you, these all algorithms works when we have redundant data. Compression ratio of 50% or more is expected with this algorithm. Compression saves screens as well as display generally show very good results. Then we have the disadvantage of LZW algorithm, as the implementation of algorithm is complicated because of the management of the string table. We have to store the string as well as its index value. The file that does not contain any repetitive data at all cannot be compressed much. In fact, if there is no redundant data, then the compression algo will have more bits as compared to original bits. The amount of storage needed is then indeterminate, and also problem involves while searching the string. Each and every time we have a new character to be read, the string table has to be searched for a match, and if a match is not found, then a new string has to be added in the string table. This causes problem that the string table can grow rapidly. Thank you for the day.